on this computer. Thank you, Sarah. All right, and yeah, as I said, get your name into me soon. Having to go back and resubmit on Saturdays, a pain in the ass, to be honest with you. So let's get out of this. Oh, and I want to stop my share. Right? Yep. Okay. So welcome everyone to today's festivities. We will be talking about indeterminate structures, and my guest is a good friend and a renowned, if I may use that word, a renowned structural engineer in the entertainment industry. It's Bill Gorlin, who is your title is head of, are you VP of entertainment, or what's your?
Yes, yeah, VP of the entertainment division at McLaren Engineering.
Right, at McLaren. So, and they, you've seen their work many times. The list goes on and on, but it starts at Cirque du Soleil, and down at the very bottom, he does work for me on occasion. So there's full disclosure on that one. Bill is going to talk with us about indeterminate structures today, and I've had a bit of a preview, and it's going to be an interesting conversation. There are a number of us here. We're 44 of us so far. I would ask that comments, questions be put in the chat. Both Sarah and I will be keeping an eye on that. I would prefer that you did not unmute and start asking questions out loud, because it'll be a bit disruptive with this number of people and with the amount of information that Bill is trying to get through today. So, but if we ignore your question for longer than you can stand, then you can yell at us, and we'll go from there. Okay. I don't have any other housekeeping stuff. Keep your mics off unless you really need to talk. And without further ado, Bill, if you want to share your screen or do what you want to do here.
All right, let me share my screen. Hi, everybody. I want to thank you all for joining. Looking at the list of people here, there's a wide range of knowledge base of those of you I'm familiar with, and I'm anticipating some challenging questions, and there may be some things you folks know a little more than I do. I think what's going to be interesting about this conversation is determinate structures and indeterminate structures have a wide range of pros and cons, and a structural engineer may look at it a little differently than a rigger, and both of them are valid perspectives. And just as much as riggers will benefit from seeing how engineers look at it, it's actually valuable for engineers just to see it the way a rigger would look at it. So I'm actually going to encourage my staff to go on and look at the recording of this after it's been recorded. Also, just to set a context, I had an interview this morning with a prospective graduate of a structural engineering program, and we asked her what were the courses you took in structural engineering. Well, the first semester was determinate structures. The second semester was indeterminate structures. Yes. And the third semester was all sorts of stuff.
Yep. Can I get microphones turned off, please? Thank you.
Okay, so what I'm going to do, I've taken some excerpts from the rigging book that Bill Sapsis edited, and I've contributed one chapter to that, which is structural behavior. And I took some excerpts from that try to explain a little bit. On the screen here, I have a definition of what a determinate structure is. And in red, a determinate structure is a structure in which load distributions to supports are influenced by load and support conditions alone. Okay, so in terms of entertainment rigging, determinate structure is a load system supported by multiple hoists in such a fashion that small moves of one hoist do not cause large load shifting to occur between hoists in a lifting system. And that's taken from ANSI 1.6-3. a structural engineer would look at that and go, huh? I'm not sure what you're talking about. Or why are you saying it that way? And I'll explain that. But essentially, a determinant structure, if it's a straight beam or truss, it's determinate if it has two supports. Right? Very simple. Simple span. If it's a curved assembly or rectangular assembly, it's determinate if it has three supports. Okay. And determinant structures are very advantageous because, you know, as I'm reading to you here, you know, the reactions are very easy to calculate, very predictable. You don't get load shifting. They're very easy to deal with as a rigger. You know what your loads are. Okay. So, you know, actually, when I first joined the rigging working group of ESTA, I was surprised to hear that the riggers felt that determinant structures are good and indeterminate structures are bad. But I was approaching it from a structural engineer's perspective, and I had to learn that it was a good thing from a perspective as a rigger. So, you know, it is a good thing, but it's also a concern. You know, what happens if one of those supports fails? The whole thing collapses. Okay, so single point failure is a concern. In indeterminate structure, and I'm not going to start going on and on with more written stuff. I'm going to give you a little example right after this, and I want to get the screen. I want you to be able to see both red. Can you see the red at the top and the red at the bottom? Just
Yeah.
some head nods. Okay.
Yep.
So an indeterminate structure, same language, is a structure in which load distributions to supports are influenced by load and support locations, as well as by the structure's stiffness. Okay, and that's really the difference between the two. And if I have if I have a beam spanning if I have a truss spanning two chain hoists, if it's a 12-inch truss or a 20.5-inch truss, it's just spanning from one chain hoist to the next, that doesn't influence the loads. They are what they are. But the stiffness is important when it's indeterminate. I want to give you a real world example, okay? And I'm going to move my camera for a moment, so bear with me as I reposition the camera. I hope I get the orientation right. Let's see, do I? And I'm going to, got some toys, okay? I went into the closet and found all the toys that my kids have. And this is a plastic track for a little, I don't know, a little pinball type thing, and they make a roller coaster out of it. And what's interesting, see this little red thing? So this little red thing is a snap-on connector, okay? And it has two notches on one side, two notches on the other. And you can see that the little green nubs are attached to the red connector with, you know, this track in my right hand. And to connect the track in my left hand, I'm going to line up those two nubs, snap them together, and now I end up with a spliced piece. Okay, that's giving me bending resistance in all directions. You know, pull apart axial resistance, bending resistance in this direction. It's a full moment splice. Okay, so let's, you know, I have three supports, right? And the blue's in the middle. And if I load both of these, you can see that I have a smile type curve under the loads, which are my fingers, and I have reverse bending over that support. The stiffness of that connection is really helping me out. Notice at the ends, it's just supported in a fashion that can rotate, because there's nothing keeping it from rotating. Now, interestingly, if I put a load on one side, notice the other side pops up. The weight of the track is insignificant compared to the strength of my hand, and it's just going for a ride. But essentially, this is acting like a hinge support or pin support, ignoring this one. That's what happened if you had a chain hoist condition. If this were a structure in a building where everything is tied down correctly, I'm going to try to get this in a better view of the camera. And I hold this side down and I load my right side. Notice at the left, I still have a reverse curve going over that intermediate support. I have to hold down my left-hand side. If I let go, it's going to pop up. Okay, so the stiffness of the whole thing really influences the behavior. As a matter of fact, if I shift this over a little bit, it's harder for me to push it down with my right hand, but my left hand is actually not exerting as much force to resist the uplift, even though it pops up a lot. Okay. So, one of the great benefits of this indeterminate structure is that if I lose this blue support in the middle, I have a fighting chance. Now it's pretty flexible, but it's not collapsing. Now I'm going to turn it into a determinate structure, and bear with me. Okay. This little connector thing is not a perfect hinge, but I'm using it to represent a hinge where the two pieces of track meet. It's not perfect, so forgive me. But essentially, I'm getting a hinge type behavior. Now, when I put the load on the one side, it doesn't affect the other side. Okay, the little rotation of the red thing is a little bit, but ignore that. And you can see I'm getting a hinge type behavior where they meet because the rotation of one doesn't affect the other. I don't have a moment connection. If I do the same thing on the other side, same thing. Ignore that popping up. That's just the little red connector wreaking havoc. Okay. So the concern I have with this one is what happens if I lose the blue support this time? My structure collapses. There's no redundancy. Okay. I have a single point failure vulnerability in my model or my frame. But it's really easy to calculate. Okay. It's also more flexible under these conditions than, I'm going to put it back. In this condition, it's much stiffer under the same amount of load. I know you can't sense it as you're watching my finger push down on it, but the reverse curvature I get over that blue support is giving me a restraint. That is a benefit of the indeterminate structure. It's really a pain in the neck to calculate the loads. Okay. So that's a real life model. I'm going to put the camera back on the top of the computer. Bear with me while I do this. Come on.
I would like to point out that Bill would have had a more sophisticated model to work with, but I didn't give him a budget.
Actually, I like the idea of using toys and using things that people can, play with. I'll use rulers and pencils and stuff because it's stuff we see in the real world. And I like that. It makes sense to me. I'm going to walk through a little bit on a little more discussion of indeterminate examples, and then I want to actually show you what happens when we do a structural analysis. I'm going to do a sort of a live structural analysis for you. Okay. So once again, an indeterminate structure is influenced by the loads to the supports are influenced by the structure stiffness. Okay. So if you recall, I'm going to scroll up again. A determinate structure with a straight beam or truss is determinate if it has two supports. And a curved or rectangular or more three-dimensional configuration is determinate if it has three supports. So it stands to reason that if a straight beam or truss has more than two supports, it's indeterminate. If a curved or rectilinear arrangement of truss or beams has more than three supports, it's indeterminate. I should have typed it correctly. There we go. Okay. So good thing that we're using Word instead of PDF. Okay. So the main advantage of indeterminate structures is that they mitigate single point failure concerns. They don't completely solve the problem, but they give you a fighting chance of survival. Okay? In a critical structure, it's very important to avoid structural failure or progressive collapse if any one element fails. So for example, in a high-rise building, or a really critical building, they will actually go do an analysis. Okay, if I take out this one column, does the structure collapse or does it hold itself up? But now let me try the next column. And they keep going around one by one, taking one out at a time. And structural engineers will do this. Now we will take lower safety factors under those conditions and maybe reduce live load because it's less likely it's ever going to happen. And if it does happen, it's probably in a very extreme situation, but it gives you a level of redundancy that gives you added level of safety. It's especially utilized in earthquake design of buildings and other structures to have that redundancy if one member fails. In fact, they do analyses where they will actually design and detail things to fail so that the first thing that fails doesn't get everything else to collapse. I've had one of the projects I did, which we were very concerned about failure of an overhead circular truss. We rigged it with 5 cables to the winch, so that if any one cable broke, we'd still have not only a structurally sound system, but a stable system in which it would not flip over. So that's an advantage of an indeterminate structure. Okay? And as I showed you before with my, with my little toy here, that indeterminate structures can be used to improve stiffness for the same member size and the same span, if you use them wisely. One of the disadvantages is you've got to bring in someone who is qualified to do the structural analysis. Could be a rigger who's experienced with it. I've known some who are outstanding at doing this. Generally, it'll be a structural engineer who's able to act, has the tools and education to accurately determine the member forces, deflections, reactions. Okay. Here's a couple of examples I want to share with you, and then I'm going to show you the analysis. So, for concert style rigging, when you have a series of hoists for a determined structure, the hoist may run at a different speed. That's going to start throwing load around. You want that indeterminacy of the structure, and perhaps having some reserve capacity in the, how close you're taking to the limit of the strength of the structure can help you deal with that load shifting that may happen as you're raising up the structure. Okay. Interestingly, and this is something I really had no idea until I joined the rigging working group, that flexible aluminum trusses is a good thing, because it allows the redistribution to happen without attracting really large forces when you're hoisting up a truss rig in a rock and roll setting, or a theatrical setting. As a structural engineer, my knee-jerk reaction would be, oh, make it completely stiff. Well, in that case, you may end up with a chain motor that goes slack. But when you have a relatively flexible structure, that it can give and take, give a little bit as you're running at uneven speed. So there is an advantage to that in that kind of system. However, what happens if you have an LED screen that's tracking, and you want that LED screen to look level and have, and not to, separate and show black lines? In that case, you do want to have a stiff structure. So, that's a rock and roll situation in which the flexibility is not good for you. So the stiffness of the structure influences you plus or minus depending on what your goals are. And it also influences you based on, what kind of support you are and the numbers that you're working with. So let me switch over to an image. Okay, let me bring this over to the screen. Okay, this is a screen grab from the Tel Aviv video that we'll see later in this discussion. And we're going in that Bill's going to explain the test apparatus. But what we see here, it's a little grainy. I apologize for that, but we see 3 chain hoists supporting a truss. And so I look, and then there's these little overhangs that aren't carrying anything. So let's just ignore that. In my world as an engineer, truss supported by 3 chain hoists. Now what I'm going to do is show you how I visualize this as a structural engineer. So I just overlaid on top of this some lines. So I've idealized that truss as a red line. And the red line has nodes, which correspond to the location on the truss directly beneath where the chain hoist attaches with the round sling. So I have a red dot representing the node. I have a red line representing the member. I have a green triangle that represents the support. Now, it looks like the support is from below, the way I've sketched it. In this case, we all know the support is from above, but it's still support, it's still gravity. Okay, so it's irrelevant. The blue arrows represent load. In this case, I placed them mid-span between the supports because it looks nice that way. So this is showing you how the computer model is emulating the real world. Now I'm going to show you my computer model. Okay, this is a program called RISA 3D, and what we have here, you zoom in on this thing, it's type. It should have schedule 40 type. Okay, and I can click and make it look like it has colors, or make it look like a stick. Let's take a look at it from the end, from the front. Once again, you see these little triangles representing supports. The one at the end has an extra little symbol to keep it from rotating, but it's the same type of support. And this is an indeterminate structure. Okay, it's continuous across the center support. I'm going to put some loads on it. I'm not going to use that one. I'm going to use that one. So I have two spans of 10 feet. I have loads of 100 pounds apiece. Okay. If this was a determinant structure, I could say, well, if I'm mid-span on this truss, half the load is going over here to the left, half the load is going to the middle support. And then for the other 100-pound load, half the load is going to the middle support, half the load is going to the right. So my reactions would be 50, 100, and 50. Actually, what I'm going to do, I'm just going to modify this model right now. And I'm going to say end release. Can you see this, or is it too small to you, folks? Bill?
It's fine.
Fine, okay. Right now it says fully fixed. I'm going to click pinned and pinned supports, which is a hinge type behavior. And you can see there's a little circle there that says, hey, this is hinged. I'm going to do the same thing on this side. Now I'm overdoing it at the supports, which are already hinged, but it's a nice graphic. So I'm doing it. And then I'm going to run this model. And I'm going to show you the results. Bear with me. I have to click a couple buttons here to select what I want to see. So this was, I pre-planned the model, but it's all happening live. And what do lo and behold, this is what you would expect. 50 on the left, 100 in the middle, 50 on the right. Okay. Now I'm going to go back to what it was at the beginning. I'm going to fix the middle by fixing all of those joints. Okay, now we're going to run the same exact analysis. And look what happened. The middle attracted more load, and the ends gave up some load. And that is a result of the indeterminacy of the system. Now, we structural engineers would say that you generally lose 15% of the reaction at the end when your next support over is fixed. And we actually lost more than 15%. It was actually quite a pretty substantial amount that got dragged over to the middle. So you can see it's wreaking havoc. If I played around with my loads, oops, oh, that's on the wrong screen. Let's get it over here. Also on the wrong screen. Let's say I screwed around with my loads a little bit. I'm going to move this load from half way on the span to, oh, that's good enough. I think I got it right. Yeah, there we go. Now I shifted that load over. I'm going to go back to a pin condition. Okay, so once again, same span, same loads. The one on the left moved closer to the left. It's not 25% of the span over. So I would assume I've got, if this is 25% of the way over, it's 75% of the load that's going to go to the end here, which is 75 pounds. And the remaining 25 will go to the middle. And then this other 100-pound load will split 50-50. Let's take a look at that. Yep, there's my 75 that I predicted. This 75 is equal to 50 from the right side, 25 from the left. Easy to predict. Now let's make it fixed again. Let's run it again. Okay. I've got, instead of 75 on the left, it's now dropped down to 60 pounds. On the right, it dropped down to 35 pounds. If you remember when we were centered, when the loads were centered on both sides, the end reactions were 31 pounds. So this 100-pound didn't change its location or its magnitude. On the left side, the 100-pound moved closer to its support, changed the reactions on both supports, but it actually influenced the reaction on the other side. So it's wreaking havoc with the distribution of loads. I'm going to show you one more thing, which I should have done from the beginning, but I forgot. I'm going to show you a deflected shape magnified 40 times. It's going to be a pretty significant magnification. So you can see that reverse curvature over the support, which is similar to the toy, that is influenced by the stiffness and influenced by the location of this thing. Bill, do you have any questions for people? Because I have to tell you, I could go on for hours with this stuff, exploring lots of ideas. I don't want to bore you folks.
You are clearly not boring anyone.
Okay.
They are hanging on your every word.
Okay.
If you'll pardon the pun.
Yes, hanging is good when using chain hoists. Bill, do you have any questions from the group?
I do not have any questions at this time, but let's pause for a second and let me ask. Well, James Lyle is asking, how would you do the math? And that's the question. So I'm not sure how to interpret that.
Well, that's a really good question. How do you do the math? The best way is to hire a structural engineer to do the analysis for you. There are some rules of thumb. Bear with me because I'm winging it now. And I got to get a view in which I can see myself. I can't see myself here, but
You're still the same.
yeah, no, I just need to be able. There we go. I can see. Okay, I get it. I have this is the Manual of Steel Construction, and there are also many other books that have guidelines. Give me a sec here. I gotta find this section on beams.
While you're looking, I should. Tansy has suggested that we get Risa to do the math.
Risa, that's what we're using. We're using Risa. That's the software. Well, here's an example. Well, let me find a good one. Well, here we go. These books contain useful tables that will give you sort of prepackaged equations for common situations that you come across. So, for example, I'm trying to read this as I'm showing it to you. This is a good one. This one that I'm pointing to with my three fingers and my right hand. So this side right here, this one right here, that's a two-span condition like we're dealing with a point load at the middle on one side. And that will get this happens to be helpful in getting that answer. What you could do in this case is you could do the analysis for the 100-pound load in the midspan using this one. The one down below.
Hey, Bill.
Location. You could do that for one on the left side and then combine the results.
Hey, Bill.
Yes.
It's been suggested if you want to unshare your screen, it'll be a lot easier to see you and the book. I don't know if you.
Oh, that was really kind of dumb, wasn't it?
I don't know if you want to go back and forth or not, but.
Yeah, I can do that.
Okay.
Can you see me now?
Oh yeah.
Okay. Sorry. All right. Let's start that again. Okay. So you should have said it so earlier, Bill.
Well,
okay.
I was listening.
Okay. So Manual of Steel Construction. This is a very old one, but it's the one I happen to have here in the house. So my newer ones are at the office. But all of them have a bunch of tabs. And the tab I went to is the beam section. And you'll find this in lots of structural engineering textbooks manuals. I wouldn't be surprised if, engineering for the stage has these tables, and there's a whole wide range of tables. Some of the more simple ones at the beginning, give you sort of basic beam equations. There's a beam at mid-span of a simple span beam, and then you have another one with one load anywhere on the beam, and there's a two load on the beam, and there's all these useful tables that give you the reactions and the bending moments and the shears. If I go farther along, there are some examples with two span conditions, which are on this page. And so a nice example is the one in the middle. That's the one I've been analyzing, actually, the two span indeterminate system with a point load in the mid span of one side. That can be used for the 100-pound load we have on the one side. Okay, those are the results you would get for that load. The one on the bottom is a more generalized condition of a single load anywhere on one of the two spans. Well, that could take care of that can address the one where we're 25% of the way away from one end. You can just combine the loads. So these are very, very useful tools. It doesn't give you everything, but it definitely gives you some help, and it also gives you a flavor for how the behaviors change as you're using these different types of loads. There's another useful table. Well, these are some other these other tables from a qualitative standpoint are very interesting in showing you how the things behave under a variety of loads. I mean, the one at the bottom, this one's very interesting because that's a 4-span continuous beam with same spans, uniform load, this one. But if you notice at the end, this bending moment is really bellied, whereas the ones in the middle are less bellied. And it's just telling me that the stiffness in the middle is pulling load to those intermediate supports. Notice that this is higher peak than that one. This is pulling a lot of load from here. My goal here is to give you sort of a feel for these things. This table here, if you ever see this in the steel manual, is a bunch of multiple spans and multiple loads on spans and extrapolating a uniform beam to multiple point loads. And eventually, if you have an infinite number of point loads, that's a uniform load. So these are some useful tools to at least help you get there.
Okay. I have a couple of questions from the audience, from the group.
Go for it.
Okay. Gotta scroll back here. Lucas asks, a lot of times other departments do not want you to move their gear. Would making offset bridles at the ends help?
Would making offset bridles?
I think he's referring to your indeterminate three hoist structure with one of your loads closer to the end.
Mm-hmm.
So, and Lucas, correct me if I'm wrong, but I think what he's talking to is taking a bridle down from the hoist rather than just a sling straight to the truss. He's talking about bridling the hoist down to the truss with unequal leg bridles.
Correct, offset bridles.
Oh, I see.
I have a picture here.
You want to show the picture?
Oh, should I share that? Oh, it says unable to participate.
Up.
Yeah, we just saw you. Look, yeah, there you go. Yeah, okay, I see it.
Like that to help with that center pick.
Yeah, I mean that can be very helpful in a couple different ways, right? What you're doing is you're helping pick up that truss if you have a flexible truss. Mm-hmm. It also gives you sort of an alternate load path. As a truss to flex, that bridle going to the center part of the truss is going to help pick it up better. It's going to give you some redundancy. So yeah, it can be helpful. It's really hard to figure out what's really going on
right.
with that, because not only are you dealing with the flexibility of your truss, but you've got a chain hoist that's hanging up in the air, and you have the possibility of pulling it sideways a little bit as a load is pulling it.
Mhm.
So I think it can be very helpful to take some of the deflection out of the truss, if that's your objective.
But say if we know that the, say, audio or whoever lighting, they're like, we have to have this specific position here. We know that it's that specific load. We know that motor's gonna take a lot more capacity than the other two, and we did the math. That would be a viable option though, right?
That's a viable option. That's a great approach. I agree.
Let me
Yeah.
let me point out, if I may. Eric brought up a point, and I share his concern. Depending on the loads, I would be worried about the tension on that very flat path, that very flat bridle. So you're gonna see some. You have to pay attention, is what I think Eric is saying, right, Eric?
Sorry, had to mute. Yeah, exactly. It just without, and I think it could be a viable solution for some situations, but depending on the loads. Plus, it's also going to pull your hoist out of plumb, and there's a bunch of other things it's going to do. It's going to do some weirdness there. Another thing that, and I'm sure you've seen this, Lucas, is doing an inverted bridle, right? And that's what I think Bill was talking about earlier, where you come from the bridle down to a couple points along the truss, which you lose a lot of room, but is another option sometimes too.
Right. Yeah. And then, just thinking about it as you said that, obviously moving the points in and doing a better size bridle, not so flat on one side, would be another situation. But
Yeah, it's really interesting because in some situations having a determinant structure is great because you know exactly what forces you're dealing with, especially in a place where like your roof structure is very limited on what it can handle, and that gives you the predictability. And of course, if you're using load cells, then that helps you with an indeterminate structure.
We'll get to that in a bit. Pedro,
Wait, can I ask you, somebody pulled up, I saw one of the chat comments, but I also part of it relating to what's available in Harry Donovan's book. I'm curious what's in there.
before you go there, I have one question previous that I don't want to get out of sequence. You know what I mean? Pedro has asked, would there be average values of stiffness of aluminum trusses that could be used in a formula to obtain an approximate result a little more accurate than the calculation that is usually done without considering stiffness? If that was too much, it's in the chat. You can go and read it.
Yeah, I did want to. Yeah, I mean, it's that's a good question. I mean, even the question of how stiff is an aluminum truss is a 12 by 12 is like black magic as far as I'm concerned. It's not really a truss. It deviates so much from a truss that its stiffness is wacky. A 20 and a half, the other ones in that range, their stiffness is more normal because they're more like normal real trusses. That's a whole other story. But I mean, I would calculate the stiffness of a truss based on the classic moment of inertia of the four chords, and then I would shave a little off because it's not the configuration of the truss is kind of wacky. I don't know. It's one of these things where I mean, the best answer really is load cells are really your best friend. Once if they become more readily accessible and in use, then you almost don't have to worry about these things. But I think the key thing, as far as I see it, is recognizing the behaviors, and even more so than predicting exact numbers. I think it's a really important thing.
Okay, why don't you go to the Harry Donovan comment?
Yeah,
not that Harry made the comment. Let me be clear here.
Somebody made a comment about what's in the Harry Donovan book. And it says Harry Donovan's book has a relevant discussion, provides both mathematical and successive approximation approaches. That's great.
That was me, Bill. There's a lot of, I mean, I just pulled it out. I don't know if you can see. But there's a lot of stuff. And one of the things that Harry does throughout, especially dealing with stuff that is hard to mathematically calculate, because he's talking in the real life, out on the road, rock and roll world, is kind of intuition and successive approximation tricks to get us into the ballpark. There's lots of stuff there. I won't do a talk through of it, and I'm just kind of leafing through it now. But it's from the rigorous perspective, not from the engineer's perspective. It kind of points you in the right direction.
Okay,
Sure.
thanks, Jonathan. Eric,
All right.
do you still have a question? I see in the
Oh.
chat.
I'll table it for later, let you get through some stuff. It's related to what Jonathan was just talking about. I'll wait.
Okay.
Okay.
And one more, and then we'll move on here. Michael asked,
Okay.
does 12-inch truss approach the reaction of a beam?
It matters what you're talking, what the context is. I mean, if it's determinate, it's the same thing as a beam.
Right.
If it's indeterminate, it's really about stiffness, and stiffness is relative. So in this, my little model with the with this, both on the computer and with this little track, it's how stiff one thing is relative to the other. And if the whole this plastic track I had, if all of it was steel, the distribution of loads would end up being the same because it's the same relative stiffness of one to the next. The relative stiffness changes when the material changes, when the sectional properties change, or when the span changes. So it's a whole relative thing. So, if I have a 12 by 12 fastened to a 20 and a half, if there was a way to do that, actually mod truss, 6-inch mod bolted to 12-inch mod, that's probably a more realistic thing, then they will influence one another in terms of, one being stiffer than the next, or aluminum and steel mod, bolted to one another. So,
Okay.
yes.
Hey, Bill, we've got 45 minutes left in a formal session. I'd like to save 10 or 15 at the end for the Tel Aviv video and that discussion.
Okay, got it. I'm going to share I'm going to grab the screen again, which I think I'm supposed to do. Okay, just so in case you guys are curious, I've built up a whole bunch of models in here and could go through a whole bunch of examples of, here's our 2-span continuous, which is the one we had been looking at. And if we wanted to extrapolate that to a 3-span, this is one of the examples I actually showed in the book, pretty much, where those 2 intermediates do a lot for you. I don't know, and also here's an example of a 3-span where each one is hinged. And you can see not only does the one where all hinged or pinned have very predictable reactions, but you can also see the deflections are significantly more for the same member. Same span, same load, same member, same material, same everything, except this model has pins. And this model on the left they're continuous over the supports, and that has a much stiffer reaction. Okay. The only other thing I'm going to throw at you, and I don't think we have time for this, but we could get into it later, is what happens if your supports are springy? Okay, this model on the bottom compared to the one on top, these are identical. Same member, same material, same load, same span, continuous over the supports. The only difference is this support on the 2 supports on the right are springy, meaning if I put 1,000 pounds of load on them, they mathematically deflect 1/2 inch or 1 inch, something like that. How would this relate to what we do? Well, let's say you're in an arena, and let's say that this hang condition, the 2 left chain hoists are connected to the primary roof truss, and the 2 right chain hoists are connected to very minor beams in the midspan of those beams. And those might be quite flexible beams. Well, that flexibility is going to influence the behavior of the whole thing, which also relates to the flexibility of the truss that I'm hanging, which then influences the reactions. So it can get doubly crazy, okay? And it's just something to look out for. So when you're rigging in an arena or any environment, just be mindful of the stiffness of what you're rigging to.
I have a question from Hugh. How does a bolt connection or a spigot connection affect the stiffness of a truss section?
Great question. I'm glad you asked, Hugh. A spigot, okay, there are engineers out there who would tell you that you can only use spigot connections because that's a real truss splice and then the end plate connection is bogus, it's foolish, you should never use it. And okay, that's from the perspective of structural purity. Okay, the spigot connection gives you direct connection from cord to cord of a truss. So therefore it's much stiffer. It utilizes the capabilities of that truss much more than a plated connection. A plated connection, the load goes through the cord, then it travels down through that plate, and the plate's flexing into the bolt, into the next plate, that's going to flex to bring load back up to the cord. That's at the top cord. And the bottom cord, you've got the same, but in reverse. It's much more flexible, and you're not utilizing the strength of that truss. So, for example, I think from my recollection, we've seen that spigoted truss is more than twice as strong as plated truss for the exact same truss. And it's all about the connection. Okay, stiffness wise, the spigoted truss is a little more stiff because of the nature of the connection, but it matters whose truss you get. Some plated trusses are reinforced with with an angle instead of just a plate. Those might be a little bit better. My boss for years kept saying to me, I don't want to see any more of those trusses that don't have diagonals aligned. They can't use those 12 by 12 Tomcat trusses. It's crap. Make them use a real truss. And then I tell them there are 10 billion of them out there like that. You really can't overhaul an entire industry. The trusses are made that way because it's easier to make, and it makes it easier to place clamps for lighting instruments and other things. And that's very important. So it's a compromise between structural purity and functionality and fabrication. He finally gave up on trying to change the whole industry. So. Good question.
Wait a minute, Mel gave up on something?
Well, it took a while to get Mel to give up on something. Anyway, this example here about the springiness of supports can get really wacky, but I think it was important to show you the difference between a purely, infinitely stiff supports and the reactions versus springy supports and the reactions. I'm going to give you one little additional example. I'm going to take this support and I'm going to make it really, this is the pinned one that we're looking at here. I'm going to make it a really springy support. Okay. And now I'm going to rerun. You see that little springy icon on there? And now I'm going to rerun the model.
Yep.
It deflected a whole lot. But because each span is determinate, the loads didn't change. Not at all. Even though it's stupidly flexible. Okay. So anyway, that's the moral of that story. I should probably stop here because this can go on, but I'll keep the software open so that nobody else at McLaren steals it from me because we have floating licenses. Okay. Now let's go. You remember this image I showed you, right? We can see the engineer's model in the various bright colors overlaid on the photo. So with no further ado, Bill, is this a good time to switch to you to
yeah, we can do that. We can do that.
Yeah, I'm going to stop my share.
Okay. Well, let me share my screen. Get the desktop here. We go riding through Death Valley for a second.
Go from one desert to the other.
Right. Come on. Get rid of my chat here for a sec. So let me give you the run up to this video. This video was made in 2007 in Tel Aviv. And the impetus for this was in the rigging working group in the ANSI standards program with ESTA. We had just started working on a standard for chain hoists and getting into it and trying to figure out how to write a standard. We realized that there was a lot of information that we simply did not have, and we needed to get that information to be able to write the standard. A company called Elon Engineering was a member of the working group at the time, and they graciously offered to conduct some tests in Tel Aviv to to get the information that we were looking for. And that's what they did. And they invited me over to be, as the American, the standards witness. I was, keeping, taking record of the whole thing. We found out a lot of stuff. We found out stuff about chain hoist that we needed to find out. And we also found out some other stuff that we had no clue about. And this is where I take the engineers to task, because it was during this particular experiment, this series of experiments, that we discovered, or at least the rigging world discovered, indeterminate structures. And it scared the hell out of us, to be honest with you. And we turned to the engineers and said, what is this? What's going on here? And the engineers in the room went, oh yeah, we've known about that. Yeah, that's normal. And there was, you never bothered to tell us. I mean, we've been hanging stuff like this for years, and you never bothered to tell us it was maybe a problem.
Engineers communicate like crap for the most case. You've got to really teach them how to talk to humans.
That's true. Yeah, I'm afraid that's true. So this is a significantly edited version of a longer piece that Elon Engineering put out. It was an informational and marketing piece. They let me edit it down for my purposes, and or Sarah, I should say, has edited it down even more for our purposes today. All we're showing are the experiments that relate to indeterminate structures. If you want to look at the overall thing, I believe it is still on the Elon Engineering website. It goes on for a while, but this one's only a couple of minutes long. So, without further ado.
In its January 2007 meeting, ESTA Task Group on Chain Hoist Usage decided to have its member, Elon Engineering, conduct an experiment aimed at measuring loads and load distributions that occur in day-to-day stage rigging scenarios. On March 5th, 2007, an experiment was conducted by Elon Engineering in the Exhibition Center in Tel Aviv, Israel. The purpose of the experiment was to check the forces and loads involved in acrobatic shows and in lifting and hanging sound and lighting equipment for entertainment purposes. The experiment was conducted in the presence of Bill Sapsis of Sapsis Rigging Installations USA, and with a special system which enables 25 measurements per second. Experiment 1. A structure of 1 truss with 3 loads and 3 hoists. Experienced rigging personnel attempted to level and balance the truss. When using the load cells, we could see that the attempts to balance the truss visually resulted in random balancing and imbalanced load division on the hoists. We also noticed that the slightest operation of one of the hoists, even for a fraction of a second, resulted in the addition of hundreds of pounds, while the truss still appeared to be balanced. Conclusion? A visually balanced structure is likely to have imbalanced load division, and some of the hoists might even be overloaded. Experiment 2. A mother grid structure was erected. The upper grid was suspended from the ceiling by 4 identical chain hoists, simultaneously controlled by 1 switch. 1 load cell was hung in line with each of the 4 hoists. An identical arrangement of grid, hoists, and load cells was suspended from this upper grid. In the experiment, a slight change in the weight of the loads on the lower grid triggered a practically incalculable change exhibited by the load cells. Conclusion? On a mother grid structure, any changes in the lower grid load or load distribution will usually change the load values and distribution on the upper grid, which in turn might cause an overload situation.
And that's that. Do we want to do that again, or can I give the screen back to Bill?
Move on.
Okay. Bill, do you want to follow up on that, or do you want me to do a little post?
You know, why don't you take a stab at it, and then I'll react to it and give
Okay.
you sort of my thoughts after you
Let me
give
get
your
out of
thoughts.
screen share here. Okay, so the frightening part about that to us as we were evaluating the results of those tests were that what those tests were telling us seemingly was that all of our previous attempts to attempt an equal load distribution were in fact not effective at all. We really did not know what we were doing. We had no idea where actual load distribution was. And this was because we were doing it in it was old school. We were measuring, or we were eyeballing architecture in the building to line up the truss with the architecture, grabbing the slings, the round slings coming from the hoist, and feeling if they had equal tension across the length of the truss. And the reality was, it looked good, but we had no real clue but where the load distribution was actually going. As I said, it was surprising and somewhat frightening. But once we became aware of it, we became more cautious, if you will, and more careful with our measurements and the way we loaded structure. I have 7 questions in the chat, so let me go over here. Bill, finding it hard to hear me. I'm sorry. Could you, Bill Gorlin, could you hear me?
Yes, I can hear you.
Okay.
So to react to that, I mean, yeah, it's one of the almost mysteries of our business. I mean, I think I'm going off on tangent for just a moment, but don't let me go too far, is, the Aluminum Association manual and their allowables for loads. We've often debated them. Sometimes they just don't seem to make sense, especially for heat affected stuff. But it may turn out that their allowables are quite low, and that's what's been saving the ass of this industry, is that where they don't let you have very high stresses on things, and perhaps they can handle a little more than we're putting on them when we're predicting things. But when we're predicting things, we're predicting low on the worst case hoist. So I mean, what's interesting about watching that video, it looked to me like 12 by 20.5 box truss.
Yeah.
And I bet you if you had 12 by 12 box truss, the numbers wouldn't have been as off, because it would have been more flexible and would have not had as much extreme load sharing.
Right. That may be.
And then,
what it said to me anyway. And let's remember that this video was taken in 2007. We were hanging big stuff in 2007 relative to the stuff that we were hanging in 1997. But it's still, I question whether from a day-to-day activity, a fashion show, an industrial, that sort of thing, whether we were really maxing out our systems where uneven load distribution could have caused a catastrophic failure. But as we moved on from 2007, we certainly started ratcheting up on our loads, and we became more careful. I know that for us on fashion shows, one of the things that we started carefully looking at was where we were running our cable, where lighting and audio and hoist power. Typically we ran it, if it was in the downtown Armor, we ran it upstage right, because it was going to go down to the floor and out the door or out the window to the generator, right? And so it was easy to run it all over there, which meant that I had a 1 ton or a 2 ton load with all that cable running off of one point on the truss. We don't do that anymore. We distribute it better, just to cut down on the possibility of sending too much load to that particular area inadvertently and causing some kind of a catastrophic failure.
From we engineers looking at this, we'll in the past, we just looked at the numbers and didn't stop and think about, the bumping and the load redistribution. And so we were equally cutting it too close. And, it's an interesting dilemma, is if you have that redundancy, which is good, then you may want lack of stiffness to allow the load sharing to be a little more, modest, right? But then you can't get things leveled as easily as if you have a more stiff assembly. So it's a little bit of a catch-22. If you were to really take a step back and say, well, what are we doing right? What are we doing wrong? I mean, once again, as an engineer, I would say, all chain motors should be winches. A nice, smooth electric winch. That's ignoring the economics of it and the history of it. But have something that's a little more precise. Not, once again, that's an academic mindset. That may not be a practical mindset at addressing that issue. One thing we have done is, more and more is required load cells, especially on a big show during tech, to make sure that the head rigger is able to say, okay, these are the loads I'm dealing with, and know that they've got the right loads. And of course, that doesn't address the specifics of each venue you go into, and it doesn't address the specifics of each hoist that's being used at a particular location and the bumping of the hoist to get it leveled. So those are still not something we're probably doing a good job of dealing with.
One of the things that we discovered during that testing, it wasn't on this particular video, but we discovered that bumping a hoist, a 16 feet per minute hoist, bumping it, turning it on or stopping it, added about 20 to 24%, if I remember correctly, of the load that you were lifting. So you were adding an additional 20% as that, kind of very short peak load when you shock load it by starting it up or stopping it.
That's an interesting one, Bill. And you think about, the impacts of bumping, right? And I would say that if you have impacts of bumping for a grid in an arena, or a fixed point for a specific chain motor in a roof of a theater, one of them, the one that's on a fixed point, fixed direct to the roof of the theater might have higher impact because you're on a stiffer roof element. You don't have a sling that helps you out. You don't have burlap in a wrapped cable that is helping you out in cushioning. We've in my discussions with chain hoist manufacturers, I've asked them, what's the impact on your chain hoist? The first one I asked at a conference turned around and ran. The second one I asked tried to get away. I did get some feedback from someone who whispered to me, we think it's anywhere from 25% to 125% impact, depending on what you do. What we've done in our recommendations when we have a show go out is we just say that wait 4 seconds between successive bumping of the button. Where we come up with 4 seconds, I pull it out of the air, but it just kind of felt right as enough of a weight to let the natural frequency of the hoist and whatever's on it dampen itself out. Because there is definitely a natural frequency of everything. And a metal housing and stuff will have a natural frequency. And you could bump with your thumb, and on one time you could help dampen it with your timing, and on the other time help magnify it with your timing. So we just say wait a few seconds in between bumps.
Got a couple of questions for you in the chat if you want.
Sure.
All right, Michael, is all aluminum truss made from the same alloy? And if not, what are the differences in strength and or stiffness? Do you want to address?
Good question. Well, by the way, a disclaimer I wanted to throw out there is that most of you listening to this have done physical work in the theater, in the arena, for live events. I haven't done squat other than sit on my ass and run calculations or learn things from people who've actually handled it themselves. I've climbed around quite a bit, but that's about it. Just so full disclosure. Aluminum. Okay, in the United States and in Canada, we typically using 6061 T6 or other 6061 grades of aluminum. They're very similar. The stiffness is pretty consistent across the board. In England and in parts of Europe, they're using I don't remember the number, is a 6000 series aluminum. It's a little bit different. I think it's slightly stronger, but not much than what we use here in North America. The stiffness is about the same. So,
Bill, if I may ask a question along those lines, I haven't read E1.2 in a very long time, but does that identify the ANSI standard E1.2? Does that identify an alloy? That
I don't think it does. I don't think it does. I think it's meant to. And I haven't read in a while either.
Yeah,
but
yeah.
I don't think any of them say here's the alloy to use, but rather follow the requirements of the American aluminum design manual.
Right.
And in that manual, it will tell you what's acceptable. The steel manual, for example, this guy, will tell you what are the steel materials that are acceptable for use in buildings and bridges. In fact, one of the cheats that I've been doing my entire career has been DOM tube is not in here. And then the really cheap, like 14 gauge, like 1x1x14 gauge or 16 gauge tube that we love to use is not in here. It's not allowed to be used. I use it anyway. But that's because I'm a cowboy.
We won't tell anyone. David Lasky's asking, so not just a momentary, does this make you check wear and tear more frequently, knowing just how much more force they may be handling day in and day out?
That's a good, that's a terrific thing. I mean, if a show's on the tour, if a show's getting, if a truss rig is going through dynamic cycles, yeah, you should take a look at it frequently. The real challenge is going to be if you're handling, if the crew is gently handling the gear, but the hoists are beating it up and you've got heavy loads on it, are you going to see a crack develop? And aluminum does not fail in a ductile fashion very often. When it fails, it just pops. And you may not see a crack occurring until it goes. And that's the scary part with aluminum. With steel, you've got more of a fighting chance. Lucas, you said riggers are not gentle. Oh, that's not true. Riggers are gentle. Come on.
Eric's comment just above that, I think is important because what that is, in my opinion anyway, is a rigorous response to an indeterminate structure and managing that load distribution by putting a pin in a hinge, as you were talking about earlier. But what do you think about the fact that they're using flexible connections?
I think you have to stop and think about what we're really contending with, because it's not. If you just talk to if you get some structural engineer who's a good buildings person who's done, does a 3-story warehouse or office building down the street or condominium or what have you, and you ask that person his or her opinion, they'll probably say, no, you need a steel to steel connection or aluminum to aluminum connection, because that's how they've been trained. And I'd advise all of you to help guide your engineer in looking at this from the perspective of the rigger's experience. It's vital, okay? And I'm reminding you, I've had to learn from listening to folks like you about these issues because I haven't been the rigger. So this is a great situation where the engineer's got to take a fresh look at it and think about what's really going on, what you're really protecting against. And the engineer would perceive it as, oh, wait a second, this is a dampening pad that I would put into a system. That's what you've got, a dampening pad. So I think it's a great idea, actually. I think it's a very good idea. It's just, it needs to be used wisely. And we need to make sure that it has, we have the strength that works for us. Slings are terrific if used properly. And is this like a clamp of some sort that has some springiness to it, or is it part of a sling assembly?
Sorry, it's Eric. Are you talking about the flexible connections that I was talking about?
Yeah.
It's more like a structural hinge, so that when two trusses are out, that they can move up and down. Yeah.
Oh, I see what you're saying. Okay, so you can move up, or if you've got an intersection of one truss across the top of the other one, and you, instead of putting 4 cheese bros in to connect them, to lock them together, you put something that's more hinge-like. Yeah, and actually, what's nice about that is it's definitely more predictable in the behavior.
Right, and it's for situations where it doesn't matter if it's out of level, right? It's intentionally, it doesn't really matter if the thing isn't completely level. So it allows for that little bit of flexibility that allows the structure to be a little bit more calculable.
A little more compliant. Yeah, that's a great idea. It's a really good idea. I think get something on the market that's cost effective. I love the idea. Yeah. You know, we do that in buildings and bridges. I mean, if you go over a bridge, right, you see hinges and, you know, you see, you know, bearing pads that you know, will have some Teflon to let them slide horizontally, and they may have rockers to let them rotate so that they don't lock themselves into place. And those are for a variety of reasons. It might be that are related to some of the things we're talking about, and for other reasons. In a bridge, it's, you know, temperature control. The bridge span may want to shrink or grow plus or minus 1/4 of an inch. And you want to let it do that rather than to fight it, you know, with anchor bolts. So it's the same physics. It's a great idea. I'd love to see that come into the marketplace.
So when I'm stuck in traffic on the Verrazano Bridge and it's not moving, and the bridge is loaded in both directions, right?
Yeah.
And you know, when the truck goes past me and the whole bridge feels like it bounces, like feels like it's 3 feet, but it's only probably a fraction of an inch. That's what it's supposed to do, right?
That's good.
Yeah.
Okay, that Bill, when you look out your window and the wind is blowing, do you see all the trees moving?
Yeah.
Yes. Yeah, that's good. They're ductile. They're absorbing the force. They're not cracking under the their flexibility is a good thing.
Right. Lucas has a question, which is back to the subject. Where does the stress go, on the pin or at the hinge plates themselves?
Well, when you say where does the stress go, I'm interpreting that because you have more movement, what happens to that, right? Is that the nature of the question, Lucas?
Oh yeah, if it's a hinge plate scenario and our connections that the pin go through are up top, where does the force or the moment happen? Is it the pin itself, or is it those welded connections in the plate?
Right. So Lucas, the way I would look at it, I can bring out my model again. I don't know if you guys can you guys see me?
Yep.
Yeah, I mean, you know, it's either rotating at the end, right, which is what happens, or I'm gonna clamp down on it. Now I'm gonna fix it at the end. My hand is experiencing a bending moment. It's actually trying to twist my hand around. My hand's resisting it, and I feel the plastic pushing up against my hand and pushing down on my finger, resisting that because that moment is there. Now I'm going to release it, let it be pinned. Okay, and it's air. Oh, dude, that's probably easier to see. And now the determinant beam is in bending, but there's no restraint at the end. So where does that force go? I think it's, you know, redistributing to positive bending on this beam only. Whereas when I lock it, it's being restrained from rotating, and therefore I develop a moment at the support in my hand. And it is taking some vertical load. It's actually taking more vertical load than in this scenario. I hope that answered your question. I'm trying to do it with a physical model, you know? By the way, this is why I stink at electrical engineering and electrical stuff, because I need something I can put my hands on and play around with. And electrical, I never got it. Eric and Jonathan, you see that in my discussions with you on our committee, right? Comes to electrical, I'm just like, I don't know.
Yeah, I just laughed out loud when you said that. That was pretty damn funny.
Got to know your limitations.
We do have about 10 minutes left officially here, folks. If you have any questions, now would be the time.
Oh, I had a quick question, Bill.
Yeah.
From earlier, when you talked about the truss, where your boss was saying don't use that truss crap, you said misaligned diagonals. Did you mean misnoted diagonals?
Yes, you're absolutely correct. I'm glad you brought that up. So if everyone has a picture in their head of a 12 by 12 box truss, you know, the Tomcat, you know, James Thomas style truss, the diagonals stop short of the verticals. And there's actually a big gap of a couple of inches between where the diagonal hits the cord. Cord is, the horizontal part, and the vertical hits the cord. And that makes it easier to fabricate, but that also gives you a place where you can sneak a cheese burrow in between where the diagonal connects and where the vertical connects, which is the reason they did that. It also means that when you're welding your diagonal, you don't have the vertical in the way to fight each other in the welding process. So it's easier to make. We engineers look at that as a non-classic truss. Now, what a classic truss, the center lines of every member intersect at the same precise point in the chords of the truss. The reason they do that, it was easier to calculate in the old days. So, 100 years ago, actually, when I was in college even, which is not 100 years ago, trusses were always classic trusses because you could do the calculations without having to determine the bending in any member. You always assume that the diagonals had perfectly axial forces, no bending, and it was hinged at where it intersected the chords. And then the chords could be pinned from intersection to intersection. You could make it like a bunch of literally pinned members everywhere, which we've actually seen out there in the old-fashioned bridges. So you could calculate this. This is interesting. It's full circle here. The structural engineer could calculate with precision what the forces were in the members and in the connections because everything was perfectly pinned at every connection. And when you had a riveted or a welded connection, we didn't have welding way back in the day, but let's say you did, and you had a gap between where the diagonal hit the vertical at the cord, that introduces bending in the cord. And back in the day, they couldn't accurately calculate that, or it took them too long to calculate it with some modest accuracy. So they got away from that. It's also a very efficient structure. If structures in structures in compression are good until they buckle. This thing in tension, I don't know if it can hold my load, but it can hold a lot. In bending, I could probably break it pretty easily right now. So, if I were to optimize this material, I put it into tension. And if I was using compression, I'd make it fatter, but I could make it pretty strong in compression as well. And so you can make a truss in which you optimize members only in tension, only in compression. You don't put them in bending. And it's a very efficient use of the material, but you've got to get those work points to align with one another. But in the modern world, we now have analysis techniques where we can do whatever we want. We don't need to have the work points line up. So the indeterminate, here we go. So that Tomcat 12x12 is an indeterminate truss used for a determinate span if you only have 2 chain hoists. How's that for you? I hope I didn't confuse the daylights out of everybody. Any other questions? I hear quiet.
Yeah, as do I.
Okay.
Well,
I hope that wasn't overly confusing. I apologize if it was. Okay, I got a thumbs up from Jonathan. There's at least one. Okay.
Well, thank you, Bill. This has been extraordinarily helpful and enlightening. I really appreciate you putting this together. And thank you all for joining us today.
Yeah, thank you. I want to thank everybody for really good questions, good comments, which enabled this to be a good session. So I appreciate it. And once again, if I hadn't had the interactions with stagehands and riggers and shop guys, I wouldn't know my ass from my elbow in this business. I would just know the theoretical. Okay. So that's important.
Okay.
So, yeah, thank you all.
Remind everybody that we are recording this and that it will be posted on Friday, along with the announcement for registration for next week's Fun and Festivities, which will be fire curtains. I know that's just an exciting, truly exciting topic, but
as long as you don't have to use them, they're fantastic.
Oh yeah, yeah. But we do want to make sure that they work.
Yeah, yeah. Great.
Okay. Thank you all. Have a good afternoon. Stay safe out there, huh?
Take care, everybody. It's been a pleasure.
Thank you, guys. Appreciate it.
So long.
Okay, bye.
Thank you.
Thank you.
Thank you, Bill. That was great. There's still a few people here left on board.
I'm waiting to ask us if you got my email.
Which one? I got a lot of them.
No, from Miller.
Yeah, I know.
Okay.
If I didn't respond to it,
Well, I didn't expect you to today with this going on, but
yeah. Well, I'll get to it after the session is over.
yeah, okay. Good session. Thank you, sir.
Thank you.
Thank you, Bill. I guess he's gone.
I think he may have gone. Well, this is where I get to the point where I end the session and it closes it for everybody in an unceremonious manner. So thank you all. Have a good afternoon, and we'll see you next time.